ladies and gentlemen, welcome back for another round. This is Mr. Doolin. I thank you for tuning in. Today we're going to take a look at Gibbs Energy, but not the full disclosure of Gibbs Energy, but just the short and sweet of what you're going to need to do and what you're going to need to be able to explain with Gibbs Energy and delta G, all right? Because Gibbs Energy is actually my delta G. Okay, so we're going to go through a couple of things, and these are really just ways that we're going to see and be able to calculate and do things with delta G. The first one, this is Hess's law, right? And so on this one, we understand that the delta G for my reaction is equal to the sum of my delta G of formations for my products minus the sum of delta G of formation for my reactants. And so this is very similar to what we've done with enthalpy and what we've done with entropy, right? So the heat energy and the disorder, we've done this. These are going to be table values where they give it to us, remember, and these are molar amounts because my delta G units are actually kilojoule per mole unit. So very, very similar to my delta H calculations that I know how to do, all right? The second way that we might see it is actually Hess's law, right? But this is the law of summation. And so with this one, we are going to be adding reactions together. And so this is, where you have a target reaction and they give me multiple reactions that I have to flip and multiply and all that other great stuff to get, to get to my overall target reaction. And again, this is something that we've done with enthalpy, and this is something that we can do with entropy, right? Nothing crazy, nothing new. The other thing that we can do, and this is an old school one where we've seen it before, is remember that delta G is equal to negative NF E cell, right? So remember, there is that relationship where N is the number of moles of electron transferred in that galvanic cell, right? F is Faraday's constant, and so I can calculate delta G that way as well. The fourth way that we're going to be able to calculate delta G is we're going to be able to relate it to equilibrium. And so in this one, delta G is equal to negative RT natural log of K. So with this, my R value, I know with Pivnert, we've memorized my R value is 0.0821 liters per mole Kelvin.atm. I can't do that with this, ladies and gentlemen. Or I think that's liters.atm Kelvin.mole. That's what the units of R are. I can't do that with this because the units of delta G are in joules. I have to use an R value of 8.314, and I think that's joules per Kelvin.mole. All right, and so that becomes my R value, and you just have to be careful and watch when that spits out. That's going to give you a delta G value in joules. A lot of the times you're going to have to convert that to kilojoules to report your final answer. All right, and so these are a couple of ways. The last way that I've actually saved is the granddaddy of them all, and this is the one that we're going to spend most of the time, is actually Gibbs equation. So in this, delta G is equal to delta H of reaction minus T delta S of reaction. And so this is delta G of reaction as well. And so, with this, I could be given a multi-step problem where I actually have to use Hess's law to calculate delta H, calculate delta S, multiply by the temperature, and then just solve out for delta G. All right? So the big thing to understand out of all of this, ladies and gentlemen, all of it is a negative delta G equals a dynamically, if I can spell, favorable reaction. And that's the coup de grace. That's the end-all be-all, right? If I plug in all these numbers and I do all these calculations, I end up with a negative delta G value. That means my reaction, once I get it going, will be spontaneous and will occur on its own without any further input. Doesn't mean it'll happen fast. It just means it'll happen. All right? And that's the big thing. That's the end-all, be-all thing about these calculations. Now, there are a couple of things that I'm going to go through here with you. First is this Gibbs equation. Delta G equals delta H minus T delta S. I have to understand that if a negative delta G is favorable, a positive delta G is not. And so I'm looking at this equation, and this is a good example that my friend Adam Jacobson told me about. or pointed out to me when I was trying to explain this. I've got H2O, that would be a solid, right? I've got water as ice and water going to a liquid. Well, we all understand that if we go and take water out of the refrigerator and put it on the table, that it melts, right? This reaction happens. But if I leave it in the freezer, this reaction does not happen. So at what point we have to understand that when it happens on the table out in the room and it's melting, that this is a thermodynamically favorable process. It happens. That means it has a negative delta G. But if I leave the ice in the freezer, it doesn't. So that means it has to have a positive delta G. So I have to be able to look and say, all right, well, what do I know? What happens? At what temperature is this thing actually going to shift from favorable to unfavorable? Well, a couple of things I know. At equilibrium, delta G is equal to 0. So delta G is equal to 0 at equilibrium. I'm going to use that, and so I'm going to plug in 0 equals delta H minus T delta S. And what I'm going to do is I'm just going to solve for temperature. Now, it ends up being T equals delta H over delta S. You can do the algebra to figure it out, but this is the temperature. If it ever asks you to solve for what temperature does the reaction shift from favorable to unfavorable, this is how you would solve it, ladies and gentlemen. All right? Because at equilibrium, I've got that 0 value of G, right? And then we can actually go through and do that. Now, there is another table, and I'm going to go ahead and draw it up on the screen here, where it relates what the value of delta G is given certain situations of whether H is positive or S is negative. And so I'm going to go ahead and pause and put that up here. All right, and so what I've got here is a couple of tables that are going to relate. First off, we're going to take a look at our delta H and delta S values to G, all right? Now, all of this is based on Gibbs Energy equation, right? The delta G equals delta H minus T delta S. This is all up here based on that particular equation. And all I'm doing is saying, hey, if I've got a negative delta H, a positive delta S, that's going to be thermodynamically favorable at all temperatures because it will always give me a negative delta G, right? The next couple of situations, it depends on the temperature, and what's happening with that is that T delta S is either becoming more positive or it's becoming more negative than the corresponding delta H. And this is something, if you're not getting this, ladies and gentlemen, it's hard to explain in a lecture. This is tutorial time. Make sure you get those questions down. If you can't look at that equation and rationalize these positive, negative situations based on, and understand that I've got to end up with a negative delta G for this thing to be thermodynamically favorable, all right? And then the big one for you to know is that a positive H and negative S is never going to be favorable. I can never, ever, ever get a negative G out of that particular situation, all right? And then the last table that I want you to know is just some relationships. We've talked about delta G and E before in our electrochem unit, and we understand that equilibrium, E is equal to 0. Well, G is also equal to 0 at equilibrium. And then if I'm at equilibrium in these particular cases, K is equal to 1. And then just going through, I understand that if it's a thermodynamically favorable process, delta G is negative, right, which means my forward reaction is favored, which means products would be favored. My K value would be greater than 1, right, because K is products over reactants. And then my E cell should be a positive E cell value, all right? And these are things that we've talked about before, but this just kind of summarizes all three relationships for you. And so make sure you get that down in your notes. And there we go, ladies and gentlemen. That was it. The short and sweet version gives you all the situations that you're going to run across with G, and then also these last two tables, all the situations where you're going to have to explain and justify delta G. I'd make sure I had some of my explanation ready with these, and I can't just like spout out. It's not just a regurgitation of the tables. A lot of the times you got to explain the context of the question. And so we'll see some examples of those with the free response questions in class, all right? So if you have any questions, get them down. I'll see you in tutorials, and other than that, I'll see you in class.